students, today we discuss about energy. So here, what is energy? So it is defined as the capacity for doing work is known as energy. So in the case of energy, the unit and dimensions are same as that of the work. So therefore, SI units of energy is joules and C's units of energy is ergs. So the dimensional formula of energy is ml square T power minus 2. So in the case of energy, are so many forms are there. So such as electrical energy, mechanical energy, heat energy, light energy, magnetic energy, chemical energy, nuclear energy, etc. So these are the energies, different forms of the energies. So in the chapter we will discuss only mechanical energy. So in the case of mechanical energy is the sum of the potential energy and kinetic energy. So mechanical energy is equal to sum of the potential energy and kinetic energy. So now we discuss about kinetic energy. Okay. First of all, what is kinetic energy? So it states that the energy possessed by a body by virtue of its motion is called as kinetic energy. The energy possessed by a body by virtue of its motion is called kinetic energy. So in the case of kinetic energy, what are the examples? So many examples are there. First example, a bullet is fired from a gun, the bullet has kinetic energy. Second example, a wind is blowing, it possesses kinetic energy. The water is flowing in a river, it's also having kinetic energy. And a hammer, moving hammer is possessed kinetic energy. A moving vehicle possesses kinetic energy. So these are the so many examples of kinetic energy. In general, all bodies having kinetic energy. Okay. Now we discuss about what are the expression for the kinetic energy. What are the equation of kinetic energy. So now we discuss about this part. Expression for kinetic energy. Expression for kinetic energy. Now I consider a mass of the body of mass small m is at rest position. So this body is at rest position. So initial velocity equal to 0. Now a constant force is applied acting on the body. Then the body is displaced some distance in the direction of force. Then the velocity of the body is v after displacement at s. So in this case, a constant force acting on the body is travels some displacement s. It acquires some final velocity v. So the body having some acceleration. So its acceleration along the direction of the displacement. It's a displacement along the direction of the force acting on the body. So in this situation, according to Newton's second law, according to Newton's second law, F equal to ma. F equal to ma. This is equation number 1. Now, using the equation v square minus u square equal to 2as. So in this situation, initial velocity of the body is 0 and final velocity is v, and a is the acceleration. Here s is the displacement. So now in this equation, v square minus u 0 2as. So here acceleration a equal to v square by 2s. v square by 2s. So here this is equation number 2. Now equation number 2 is substituted in equation 1. We get so F equal to m into here acceleration, equation number 2 substitute in equation 1. We get F equal to ma. Here a means v square by 2s. v square by 2s. This is the force. So in this case, when the force is acting on the body in the direction of the displacement. So here displacement and force are along the same direction. So now work done. The work done by the force in this case W equal to F dot S. So that is Fs cos theta. So in this situation, force and displacement along the same direction. So here theta equal to 0 degrees. So these are the parallel vectors. So therefore Fs cos 0. Cos 0 means 1. That is the Fs. So therefore work done by the force W equal to is given by F into S. So here F means above equation m into v square by 2s into s. So therefore ss cancel is equal to half mv square. Half mv square. So W equal to half mv square. This work done is appears kinetic energy of that body. So now this work done is equal to kinetic energy. So kinetic energy equal to half mv square. Half mv square. So this is the expression for the kinetic energy or equation of the kinetic energy. So now, in this kinetic energy of the body is mainly depends on only two factors. First factor is it depends on speed of the body, and mass of the body, Next, relation between kinetic energy and momentum of the body. Kinetic energy and momentum. We know that kinetic energy equation is K equal to half mv square. So now in the above equation we can multiplying m by n in RHS side. So therefore kinetic energy equal to m square v square by 2m. We know that momentum means the product of mass and velocity of the body. So therefore in this situation m square v square, that means p square equal to m square v square. So therefore kinetic energy equal to p square by 2m. So this is the relation between kinetic energy and momentum. So in this case mass is first point. If mass is constant, then relation between kinetic energy and momentum is, so in this case 2m also constant. So therefore Ke is directly proportional to p square. So therefore here case 2, if momentum equal to constant, so therefore kinetic energy is inversely proportional to mass. So here momentum is constant. So therefore third point, if K equal to p square by 2m, so therefore p square equal to 2m Ke. So therefore p equal to root over 2m Ke. So now the relation between momentum and kinetic energy is, so here P is directly proportional to root over kinetic energy. So in this situation mass remains constant. So momentum of the body is directly proportional to square root of the kinetic energy of the body. Okay. Next we discuss about work energy theorem for constant force. Work energy theorem for constant force. First of all, what is the statement of work energy theorem? It states that the work done by a force acting on the body is equal to the change in kinetic energy. So therefore, in this situation, it states that work done by a constant force acting on a body is equal to the change in kinetic energy. Change in kinetic energy. It can be written as here W equal to delta KE. Here delta KE means final kinetic energy minus initial kinetic energy. So this is the equation. So then it can be proved that it is a proof of work energy theorem per constant force. Okay. Now proof. Let us consider mass of the body. Let us consider a body of mass small m moving with initial velocity u. Now a constant force acting on the body, then it can be accelerated with an acceleration a in this direction. Now the displacement covered by the particle with acceleration a, the body acquires velocity v after traveling a displacement s. So here v is the final velocity of the body, here u is the initial velocity of the body, here f is the force acting on the body, here s is the displacement covered by the body, here a is the acceleration of the body. So in this situation, according to Newton's second law, according to Newton's second law, F equal to ma. So this is equation number 1. So in this situation, when a body having initial velocity u, final velocity v, here s is displacement covered the body and acceleration a. So now using the equation b square minus u square equal to 2as. So therefore, in the above equation, we can find out acceleration a equal to v square minus u square by 2s. So this is the acceleration of the body. So this is equation number 2. So now equation number 2 is substituting in equation 1. We get equation 2, substitute in equation 1, we get F equal to m into, here acceleration is v square minus u square by 2s. This is equation number 3. So now when a body is traveling some distances with acceleration a, then the work done by the force is W equal to F into S. So therefore here F means m into v square minus u square by 2s into s. So here s cancelled. It means half m v square minus half m u square. So in the case, the work done is appears to the, this work done is equal to the half mv square minus half mu square. That means this one is final kinetic energy This one is initial kinetic energy. So then the work done by the force W is equal to final kinetic energy minus initial kinetic energy. So therefore W equal to, so final kinetic energy minus initial kinetic energy, it can be written as change in kinetic energy. Change in kinetic energy. So hence the theorem is proved. Okay, thank you.